so next topic connected to gravitation is gravitational potential energy, U sub G. And now when we're on Earth, when we're on the surface of Earth, we just typically write UG as equal to mgh, which is just h meaning the distance from a reference point or the change in distance. And it's pretty simple because it's just how far you would fall due to gravity due to h, or due to how far h you would fall due to the gravity mg. But when we look at the macroscopic level, it becomes a lot more complicated as the formula for gravitation is not mg, it's g m over r squared, m1, m2. And now we know that this is force due to gravity, but one of the key relationships that we have derived is that u equals the negative integral of f dt. Meaning that force, if you integrate force, you will get kinetic energy. This is dx, sorry. We know that energy is defined as the integral of force dx just because we're multiplying force times x. And then because change in kinetic energy is equal to the change in, change in energy is always constant. Whatever you change in kinetic energy has to be the opposite change in potential energy. So that's where we get this negative from, where u is equal to negative integral of f of x dx. So integrating this equation is pretty easy, but when we have a bigger equation, it's a little bit harder. But we can still do it. We can write this u sub g equals negative integral of g m1 m2 times r negative 2. And this is dx, but it's really the same thing as dr. And now, this is a constant that can go out. So we're really just integrating r to the negative 2, which by the power rule just becomes negative r negative r to the 1 or to the negative 1. So negative 1 over r. And we plug back in, this all goes out to the side, so it all becomes negative g m1 m2, and then I guess 1 over r. And we know that we're going to be integrating this from a certain r initial to r final. So when we plug in values for r initial or r final, we finally get the formula that u equals g m1 m2 times r1 over r initial minus 1 over r final. It gets flipped around due to the negative sign. So this becomes our formula for gravitational potential energy at the macroscopic level, and that's what we'll be using. All right, problem 26. This one's about potential energy of the two satellites, as we have seen in the previous two problems. Just to refresh ourselves, potential energy equals the negative integral of force. And if we integrate the equation of F equals g m over r squared, we get the formula of potential energy equals g m times 1 over r initial minus 1 over r final. Is the potential energy when you're looking at macro long distances in the situation that we see right now. So to find the ratio of u1 to u2, we can just start by looking at what u1 equals to, and gmm, same thing, g gravitational constant, m1 mass of the sun, times, we can assume that the initial, or that the final radius is, or initial radius is 0, because we're basically going from 0 from the surface to wherever the satellite is. So we just have 1 over r1, and this is negative, but it doesn't matter because we're doing a ratio. So we just get g m1 ms over r1. And if we repeat the same process for u2, equals negative g m2 ms over r2, then we can find the ratio between u1 and u2. And so we'll start up here. U1 over U2 equals GM1 MS over R1 over, all over, GM2 MS over R2. And G and MS are a constant, so we can cancel out these, and we're left with M1 over R1 over M2 over R2. Flipping the denominators to the top, we get M1 R2 over M2 R1, which is answer choice C.